What should be the definition of a curve? Consider 4 examples: the circle, the parabola, the cusp, and the figure 8. Which of these would you consider to be a curve? And, more importantly, why? It is much harder than it seems to give a precise mathematical answer that matches our intuition. In this video, you will discover a sensible definition for curves in any dimension by visually studying these 4 examples in 2 dimensions. We will focus on the geometric and physical intuition rather than the specific equations. What should be the definition of a curve? To answer this question, we need to decide what makes a good definition. Let's try to give an intuitive but non-rigorous criterion. A curve should be a bent version of a straight line segment. That's a nice idea, so let's try to rephrase this a little more formally. A curve should look like a straight line when zooming into any point, except maybe the endpoints. That's a better description, but we can make it a bit more formal. A curve should be a one-dimensional smooth manifold at every point, except maybe the endpoints. That's a great criterion. Let's stick with this idea, but there are a few disclaimers. First, there are many other definitions of curves. Ours will be designed for multivariable calculus purposes, but it will not be the modern standard from differential geometry. Second, the endpoints could be included with a more technical definition, but we're ignoring this for simplicity. Third, you may want to pause to review the definition of a one-dimensional smooth manifold, but it's not necessary. The second description will be helpful enough. Which of our 4 examples will pass this informal criterion? First, the circle. If I pick any point and keep zooming in and zooming in and zooming in and zooming in, it looks like a line. Check. It passes the criterion, so this should be a curve. Second, the parabola. Again, if I pick any point, aside from the endpoints, and keep zooming in and zooming in and zooming in, it should look like a line. Check. This should also be a curve. Third, the cusp. If I zoom into a point away from the origin, and I keep zooming and I keep zooming, it does look like a line. But if I zoom into the origin, there's an issue. So I keep zooming and I keep zooming, but it never looks like a straight line. It looks like 2 line segments getting closer and closer. By our criterion, this should not be a curve. Fourth, the figure 8. Again, if I zoom in enough into a point away from the origin, it does look like a straight line. But if I zoom into the origin, there's again a problem. It doesn't look like a straight line at all. Instead, it looks like 2 straight lines crossing. This should not be a curve either. Okay, we have decided which of these 4 examples should and should not be a curve. We need to make a definition that matches this visual intuition. The definition contains several essential properties, which we will introduce sequentially. Instead of spilling the whole tea, let's take a sip with the first essential property of a curve. A map gamma from the closed interval AB to Rn is a one-variable parametrization of a set C in Rn if C is the image of AB under gamma, and gamma is continuous on its domain. Physically speaking, this can be interpreted as an ant can continuously trace out the path over a compact time interval. This physical description is hopefully sensible because time is a one-variable parameter, and curves should only need to be described by one variable. That's what should help make them look like one-dimensional smooth manifolds. Note that a compact time interval is used to help ensure the curve has finite length. We could consider curves with infinite length, but this restriction to compact intervals will be good enough for most multivariable calculus situations. Now, let's check whether our 4 examples can satisfy this definition. Now, which of our 4 examples can be expressed as a one-variable parametrization? The circle can be parametrized by gamma of t is cos t sine t, where t goes from 0 to 2 pi. Let's put that on loop. The parabola can be parametrized by gamma of t is t comma t squared, where t goes from -1 to 1. Let's put that on loop. The cusp can be parametrized by gamma of t is t cubed comma t squared, where t goes from -1 to 1. The figure 8 can be parametrized by gamma of t is sine t comma sine t cos t, where t goes from 0 to 2 pi. You can check that all of these are one variable parameterizations of the corresponding set. The good news is the circle and parabola passed the test. But the bad news is so did the cusp and the figure 8. We want to eliminate these two with additional properties. Let's take a closer look at the cusp. The origin is the problematic point for the cusp. Is there anything weird going on with our one variable parameterization at the origin? Let's watch closely as the ant passes through. Aha! The ant actually stops when it hits the origin. Let's see that again. Right there. This observation is crucial because it reveals how the ant must walk through the cusp point. To turn around, either the ant changes velocity abruptly at the origin, or the ant stops at the origin. In other words, if the ant's velocity changes in a continuous manner, then the ant must stop at the origin. This discovery inspires two new properties that should help define a curve. First, a map gamma from the closed interval AB to Rn is regular if gamma is differentiable on the open interval AB and its derivative is not 0 for all times t in the open interval AB. Physically speaking, this says the ant never stops moving, even momentarily. Second, a map gamma from the interval AB to Rn is smooth if gamma is continuous on the closed interval AB, gamma is continuously differentiable, or C1, on the open interval AB, and its derivative is bounded on this open interval. Physically, this says the ant changes velocity smoothly and has bounded speed. Just as a small caveat, this definition smooth is not common due to the bounded derivative requirement. It is a bit more restrictive, but good enough for many situations. Which of our four examples are also smooth and regular? For each parameterization, let's watch the ant walk along the set. First, the circle. As you see, the ant never stops, changes velocity smoothly, and has bounded speed. Actually, the ant has constant speed in this case. Either way, this parameterization is smooth and regular. Second, the parabola. Again, the ant never stops, changes velocity smoothly, and has bounded speed. Smooth and regular too. Third, the cusp. The ant does stop, but still changes velocity smoothly and has bounded speed. This parameterization is smooth, but not regular. Fourth, the figure 8. The ant never stops, changes velocity smoothly, and has bounded speed. This parameterization is also smooth and regular. Now, we've made some progress towards the definition of a curve. The circle and parabola both pass this tougher test, whereas the cusp failed. Good. But sadly, the figure 8 still passed the test. We're so close. Remember, we want to eliminate the figure 8 as a curve. So let's take a closer look at it. The origin is the problematic point for the figure 8 due to the crossing. What about our parameterization allows this crossing at the origin? Let's watch the ant. So it starts at the origin, keeps walking all the way around, goes through the origin again, and ends up at the origin. Wait a second. There's something going on compared to the other points. Let's record the time that it passes through. So it starts at t is 0, goes all the way around, and t is pi, as well as t is 2 pi. The ant visits the origin exactly 3 times. And this is special because the ant visits all other points exactly once. In other words, the parameterization is not injective. But hold on a minute. What about the circle? The circle's parameterization is not injective either. It starts at this point on the x-axis, It goes all the way around, visiting every point exactly once, but then it also ends at the x-axis. The only spot visited twice are the start and finish, namely the endpoints of the time interval. We can accept starting and finishing at the same spot, because of course the circle should be a curve, but that's all we can accept. The figure 8 parameterization, on the other hand, fails injectivity in a situation other than just the start and finish. This critical observation spawns one more property which should help define a curve. A map gamma from the closed interval AB to Rn is simple if gamma is injective except possibly at the endpoints. In other words, for all s and t in the closed interval AB, if gamma of s is equal to gamma of t, then either s equals t or s and t are the endpoints of the interval. Physically speaking, this means the ant never visits the same spot twice, except possibly the start and finish. Okay, round 3. Which of our 4 examples are smooth, regular, and simple? For the circle, the ant never visits the same spot twice, except the start and finish. So this parameterization is also simple. The ant on the parabola never visits the same spot twice, anywhere. Simple. The cusp is already not regular, but let's see if it is simple. No 2 spots are the same for the ant. Simple too. Finally, the ant on the figure 8 visits the origin 3 times. Not simple. Hallelujah. We've managed to find the properties that match our intuition with these 4 examples. The circle and parabola both pass the test, and the cusp and figure 8 both fail. One is not regular, and the other is not simple. Will this be enough to produce a good definition of a curve? Much to our delight, yes it does. And we've got the theorem to prove it. Fix a set C of Rn. If gamma is a simple, smooth, regular, one-variable parameterization of C, then C is a one-dimensional smooth manifold at gamma of t for every t in the open interval AB. This beautiful theorem matches our original intention. A curve should look like a straight line when zooming into any point, except maybe the endpoints. Its proof is actually quite sophisticated and requires the implicit function theorem, a deep and scary tool in multivariable calculus. I am not so brave as to explore that right now, but hopefully this theorem we can just take on faith. Instead, let's confidently provide a good definition for a curve. A set C in Rn is a curve if there exists a simple, smooth, regular, one-variable parameterization of C. Gosh, that feels so good. Looking back at our 4 examples, we can finally identify what should and should not be curves according to our definition. The circle and parabola have simple, smooth, regular, one-variable parameterizations, so they are curves by definition. The cusp's parameterization was not regular, and the figure 8's parameterization was not simple, so they should not be curves. To actually prove they are not curves, we would need to check all possible smooth parameterizations of the cusp and figure 8, but that's a lot of work. Let's just bask in the glory of our newfound definition of curves. What can I say? I like my curves how I like my coffee. Simple, smooth, and regular.